Hello guys, welcome to another session to solve another problem in fluid mechanics. Then this problems is another one about fluid and velocity distributions in a laminar flow. But first, let me introduce the book and reference of our problems. This book is Fluid Mechanics from Professor Streeter, Professor Wiley, and Professor Bedford. This is 9th edition of the book. Let me go back to problem. Okay, number 29 is the problem I want to solve for you. Let us do it together and read it first. The velocity distributions in laminar flow in pipe is given by this relation. Okay, this is new as velocity V max as the max velocity of this pipe of the flow in this pipe, and R out as the radius of that pipe. Determine the average velocity and the kinetic energy correction factor. Kinetic energy correction factor and average velocity. We should find these two values. Let's do it. Okay. But first, let me draw the picture of that. We have a circle here as the pipe. As the pipe, we have a circle here. Okay. Then this is center of that circle. This is R out, and I have to choose an element in this circle. Okay, the area of these elements is dA, differential of area. The radius here is R. Okay, between these two lines, let me draw it for you. This is the A, a section of the A here. Here from the center of the circle is R. Okay, and what do we have? The width of that is dr. Yeah, dr. I want to calculate dA. It would be 2p r divided by dr. Is it true? The area of that one, dA equals that. This one. Okay, let's get started and solve this problem. We want to know first average velocity, and second kinetic energy factor. Kinetic energy factor and average velocity. Okay, and our formula is something like that. V max as maximum velocity, R divided by R out square. Okay, everything great. So let me start to solve this problem. we know that energy in second equals energy and weight from weight units, which is Newton. Okay, Newton. Weight multiplied by weight in sec. Okay, these two eliminates, then energy per second is be like this formula. I will use this formula to solve the problem. Okay, so you know that energy per weight unit would be like that, nu over 2g. This is a term in equation of Bernoulli equation. Let me write it. Z plus 2 over 2g plus p1 over gamma, okay, equals c. Is it true? So this term is that one, and this is this term. This term is that one. Okay? Then I want to use this term because you know that it would be meter square per second square. Okay? And we have here G, meter per second square. Well, that would be M. Okay, in this way. But in another way, I know that that it would be written like that. M S2. We add a kilogram here, and know that kilogram meter per S2 would be N. It will be equals Newton meter per kilogram. Okay, this would be like that. But it is with 2. Okay, but we have a G here, so the unit of G is meter per square. Okay, if I want to use it, it will be a kilogram here, a kilogram here. It will be Newton. Okay, and this kilogram will be eliminated with that one, and it would be Newton per meter over Newton. This is energy and this is weight. Okay, this was energy, then this was mass, but this was a Newton meter for energy and for weight. This is unit for 2 over 2g. Okay, so this is energy per weight, and we can use it here. Okay, let me continue. But for this one, what should I use for this term, weight per second? I know that I can write, you know that gamma equals weight per volume. Okay, and you know rho density as density is equal m over v. Okay, I don't need that one, I need this one. I can write it in this way. W as weight equals omega v, v as volume. Okay, then is it true to write d w equals omega b, which is constant dv. Is it true? Of course. Then write me in this way. I need to change it because I need weight per second. It doesn't have any second. Let me divide these two sides of this equation. 2 seconds. S and S. Does it have any problem? No. Then I can write dw dot in place of that, okay? Equals gamma dv dot. In place of dv dot, what can I use? I can use, I know that is would be velocity multiplied by a. Is it right? Of course. This is m cubic per sec. This is meters per second, and this is m square. These are equals. So this is actually m dot. Oh, better say this is q. We use it with q to show it. Okay. Let me just use this one, okay? But I can write in this way: dv dot equals nu dA, okay? I will put it inside that. Then dv dot equals gamma nu dA, okay? This is weight per second, and equals that one. I will use it in place of that, okay? So we go to 2G and this one and this one. Let's do it. Let's use it. Okay, then I can write energy with the y with joule per second equals integral of d dot equals integral of, let me write it again to be clear. E dot equals u2 over 2g multiplied by gamma nu as velocity dA. Okay, this is E dot. Let's do it. It is 2g gamma nu dA. This will equal gamma, which is constant, will come out from the integral, and 2g2 nu 3 dA. Okay. But let's the 2g remain inside the integral because I need to use it inside of that. I don't need these two equations. Then let's continue. I want first to write equation for a kinetic energy factor. Okay, so I can write if I imagine that we have the average velocity from this formula. We imagine that we have an average velocity. It doesn't need to integral from that. Okay, so but this is not correct. It is not true. Okay, I can write gamma nu 3 and a. Okay, I can write it exactly the same that way, but it is not exactly equal to this one. So I have to add a factor here, which is alpha, and this factor is kinetic energy factor. Exactly, kinetic energy factor is here because I want to use average velocity to be equal to this value. Okay, to be equal to gamma integral of 3 2g dA. Okay, then I want to find alpha. Alpha would be eliminate these two gamma and okay, I forget to write 2g here. Okay, then these 2g will be eliminated, gamma, and I just have these values: 1 over a integral of nu over nu bar power of 3 dA. Okay, this is a. Okay, I have to find out. Okay, I don't need this formula. Let me raise them. Let me write it exactly here. Alpha equals 1 over a integral of nu over nu bar with power 3 dA. Okay. I need to, and now I need to calculate nu bar because I don't know exactly the value of that, and I have to calculate this one. I know this one, and I have the relationship between max and R and RO, but I don't know nu bar because I need it. I have to find it. So let's do it and calculate it. I have a relationship here: nu bar multiplied by a will equals integral of nu dA. Okay, this is true. Then nu bar equals 1 over a integral of nu dA. Okay, it equals a is area of whole pipe, so 1 over p, a radius square. I should write RO square. Okay, integral of okay, integral of nu and dA is 2 P R D R as I calculated before. Okay, so is equal to these two, and this P will eliminate from this one, and the answer will be R0 square integral 0 to RO V max. I should put these relationship instead of V. Okay, R minus R3 and RO double. Because I have an R here, I will multiply this R to this relationship. It would be like that. dr. Okay, then I can, because the Vmax is constant, will come out to Vmax over R0 to, it would, if I integral from these two terms, it would be R2 over 2 minus R4 over 4 R0 2 from 0 to RO. Okay, answer will be 2 Vmax over R0 2 R0 2 minus R0 4. If I put RO in place of these two R's, the answer will be like that. Or it doesn't change. R0 2. Okay, and we have finally 2 Vmax over R2 and R2 here. 4. Okay, I will plus these two terms. It will be like that. It will be eliminated, and it would be like max 2. Okay, then our new bar is Vmax over 2. It is a practical equation. I should use it. Mu equals Vmax over 2. Okay, let me erase this because I found new max average velocity. Okay, then so far I found average velocity, new, this one average velocity, which is Vmax over 2, and I have to continue and find alpha. Okay, because I have to put Vmax over 2 and put this new in place of new to find exactly the value of alpha as numbers. This is not a number. Okay, let's do it. Okay, alpha equals 1 over P R02, because as the area of whole pipe. Okay, integral of let's get a line here. I should use this equation in place of that with power 3. Then it would be max 3 1 minus R O R0 to the power of 3. Okay, and I put V max over 2 in the denominator. V max over 2 square, 3 with power of 3 here. Okay, let me write it better. Okay, and multiply by dA, which is this one, 2p rdr. Okay, I know 2 with power of 3 will be 8. Multiply by 2, and this p will be eliminate this one. We have here a 2, and the limitation of integral is r from 0 to r o. Okay, integral of 0 r o. Just we have this one, r1 minus r over r o, to all of them with power of 3 r dr. Okay, then it would be like that, 16 r2 integral of 0 to r o, 1 minus r 0. Okay, but let me write it in this way. As you know, we have this relationship, I minus b with power of 3 would be something like that. Minus, positive, minus. Okay, 1 2 3 4. First is a3 last b3, 3a2 b, 3a b2. Okay, I will use it to write this one because it had power of 3. Let's do it. It would be, of course, I will multiply it by an r. Pay attention to that. It will be like r three minus 3 r 3 over r2 plus 3 r5 and it doesn't mean any 3 here. There are 5 r5 minus r7 or r06 dr. Okay, equals 16 r2. I should integral all of this one and put it in place of r place of a value. Okay, let me do it. It would be r2 2 minus 3 r04 4 r2 plus 3 plus 3 r06 6 r0 4 minus r08 8 r06. Okay, and don't need this relationship anymore. And okay, it would be r2 with this one. All of this will be eliminate these r's. Okay, the answer will be 16 1 over 2 minus 3/4 minus 1/2 minus 1/8 will equals 6/8 2. Alpha is 2, which this is a factor for laminar flow at the pipes. Okay, this is the second question. Thanks for pay attention to this solving and this session. I hope you enjoyed that session, and take care of yourself. Bye bye.